Examples. Now, if you want to see where these things are coming from, off you go into section 3.5.3, where all of this is done. Yeah. So the first one is, and oh, there's going to be some table of these. So there's a table somewhere, which hopefully I will send on to you sooner rather than later. Okay. So the first one, if the input function is a constant, so look at the thing on the left. So no matter what the input is, the output is 3. So I might just write here for all inputs to this function f to f, the output is the same. So that's a graph. A constant function looks like that. So imagine if it was a sales or something like that. Oh, the sales are a constant. It turns out that if this is your input function, this is your time domain function, constant, the Laplace transform will be a constant divided by s. So you have this graph on the left into the Laplace transform, and it produces this thing. So the thing on the left goes in and the thing on the right comes out. Right. Exponential function. Okay, what have we got? So if now this isn't defined for all particular values of s, but we don't have to worry about some of those subtleties. So what you have on the left is a function e to the 2t. That's the input. And the output is 1 over s minus 2. Now the usual thing we're going to have is negative exponentials is typically what we're going to be dealing with. Because usually what we're not going to want is infinities. And if you have a positive exponential, it goes to infinity. And usually in any kind of physical system, you don't have infinities, or else the time doesn't go on forever. It can be one or the other thing. So yeah, well, that's another one anyway. Here's another one. So if you put in the identity function, so this same thing, so what I'm saying is say 1 in, 1 out. 1 in, 1 in. Let's use a different color for that. Say 1.5 in, 1.5 out. Because remember that all the points on a function are of the form input, output. Okay, so anyway, if you take that function, t, the Laplace transform of it is 1 over s squared. And what happens with power? So we've got a formula here. You can do an induction, but it works something like this. The Laplace transform of t to the n is n factorial, and n factorial is like this. So for example, 4 factorial is 4 by 3 by 2 by 1, whatever that's equal to 24. Yeah, and you can try and figure out that joke below if you want. What about polynomials and stuff like this? So if you got a sum of terms, how can you do it? Now I presume I'm going to write down. Yeah, eventually it's yeah. So I think I'll probably just kind of show how I'll kind of show one of them here. So suppose for example you want to find the Laplace transform of, let's say for argument's sake, t squared plus e to the minus 3t. Suppose that's what you want to find. So that's something that you can evaluate at s. Okay, so that would be the integral from 0 to infinity. You put in the function, so that's t cubed plus e to the minus 3t times e to the minus s t dt. But integration is what's called linear. So if you want to integrate a sum, you can actually just integrate separately. So you can show that this is actually equal to the integral from 0 to infinity. You can do the t cubed by e to the minus st first, plus then you can do the e to the minus 3t, e to the minus st, and the s should still be orange. And so what is this? This is the Laplace transform of t cubed, evaluated s, I suppose, plus the Laplace transform of e to the minus 3t, also evaluated s. So what it means is if you want to do a Laplace transform of a sum, you can do it term by term. And that means that the Laplace transform is, well, that means it's additive. If you have a constant, so I could put in I'll just put in a tiny constant, say if I put in a 4 here, right? Then I can put a 4 here, and that 4 can be taken out here, and that 4 can be taken out here. So that's, you can fix constants and do the Laplace transform term by term. So that's good as well. And we're going to write that down below anyway again. What about cosines and sines? Now what you can show is, now this will have to use, this is using Taylor series from last semester. Okay, and so it comes from there. So what you say, if you want to look at the Laplace transform of cos 2t, using this formula here, you look, so the Laplace transform of cos 2t, which could be very difficult. Like, those integrals are very difficult. Now you won't have to evaluate any of them. That's the good news. But even if you wanted to evaluate this one, it'd be quite tricky. But you can use it. It's actually easier with these complex exponentials. So this is the Laplace transform of, now look at this thing. So look at the cos omega t here. So that's the first one divided by 2 plus the second. You can divide in the 2's basically is what I'm saying. So we get ei omega t over 2 plus ei omega t over, that should be minus, over 2. And the question is, like, so what I'm saying is the cos, okay, whatever, that's very difficult, but I can write the cos as a sum of complex exponentials, and it turns out that calculating the, so if I go back here, go back again, this actually works with a being a complex number, you can show. So if I want to do the Laplace transform of cos, I can do it, turn into a sum of exponentials, and now I've got what's called linearity, which says that, so the linearity tells you that if you've got a sum, you can do term by term fixing constants. So it's going to be a half Laplace transform e to the I omega t plus a half Laplace transform e to the minus I omega t. So you can do term by term fixing constants. So it's linear. Now what also is linear is differentiation integration, and that's just, it's coming here. Okay, so it just means that if you've got a sum like this and you want to find the Laplace transform, you can do term by term fixing constants. Now if you look in some texts, so I got little q of t. So if you look in some texts, they'll just go from little q of t, and they'll say the Laplace transform of little q of t is little q of s. I strongly do not recommend that. What you want to do is to kind of remind yourself that you're going between t and s, is you keep little for the t domain. So what the hell am I on about a t domain? So remember what the Laplace transform does. You take functions of t in yellow, you end up functions of s in orange. So you're translating kind of from English to French. And what I'm trying to say is to remind yourself that you're in whatever domain. On the t, we'll use little f, and on the big, we'll write big F. Sorry, in English, in the t, little f, in the French, in the s, big F. So if I'm finding the Laplace transform of little q of t is going to go to big Q of s. Okay. Sorry, I know I'm jumping around here. I just have to get this right. So let's do the Laplace transform here of this little q of t. So if I do the Laplace transform of both sides, the Laplace transform of little q of t is big Q of s. And now we do term by term fixing constants. So fix the 2. And what is the Laplace transform of t squared? So we better write down a little formula for ourselves. So it's written, I know it's on the previous page, the Laplace transform of t to the n is n factorial divided by s to the power of n plus 1. So if I'm sending t squared here, the n is equal to 2, so it'll be 2 factorial over s to the power of n plus 1, 2 plus 1. Fix the 3. Now what the hell is going on with t? Well, of course, t is just t to the 1. So we can use that formula here. So t to the 1 would be sent to 1 factorial over s to the power of 1 plus 1. And 4 is a constant, and that was done back here as well. A constant 4 is sent to 4 over s. So plus 4 over s. And we can tidy this up. 2 by 2 factorial. 2 factorial is 2 by 1, which is 2. 2 by 2 is 4. S to the power of 2 plus 1. Well, that 2 plus 1 is 3. 3 by 1 factorial is 3. S to the power of 1 plus 1 is s squared. And finally, plus 4 over s. So your very first Laplace transform. If it's a sum, you do it term by term, fixing constants. That's what linear means. Okay, do another example. So now what I'm going to do here is I'm going to write this as 4 times e to the minus 1 times t. Minus the 1 there I don't really need. I've got the 1 in the funny place. That should just be t cubed. Okay, now I'm going to write down 2 Laplace transforms. So the Laplace transform of t to the n is n factorial over s to the power of n plus 1. And the other thing we need is the Laplace transform of e to the minus at is 1 over s plus a. So we do the Laplace transform of both sides here. The little f of t, so I think we have plenty of time to take our time here. So we're going to do the Laplace transform of little f of t is equal to the Laplace transform of 4e to the minus 1t minus t cubed. Now Laplace transform of little f is big F of s. And now we're going to use linearity, kind of spell it out. What does linearity mean? It means term by term. So you can do the 4e to the minus 1t first, and you can fix the constant of 4. Laplace transform e to the minus 1t. And then the minus t cubed is minus 1 by t cubed, so we can fix the minus 1 there, just same as minus. Laplace transform of t cubed. Now what do we get? 4 times Laplace transform e to the minus 1t, use the top formula on the right. So the a here is minus 1. Sorry, the a is 1. So it'll be 1 over s plus 1. Minus the Laplace transform of t cubed using the formula on the top left. So the n is 3 here. So it'll be 3 factorial over s to the power of 3 plus 1. So the 4 by 1 gives you 4 over s plus 1. Minus 3 factorial is 3 by 2 by 1. 3 by 2 is 6 by 1 is 6 over s to the 4. And now we can find the Laplace transform of sine and cosine. So it kind of goes like this. So the formula for the formula up the middle up here, that works even if a is a complex number. So you end up with this. You do a lot of messing around. You don't have to go through this, but you end up with this formula here. So for example, the Laplace transform of cos 2t using this formula above is s over s squared plus 2 squared. And similar story, there's a formula for the sine that, and they're all in a table. Okay, and I think we'll probably, we'll keep going. So for example, just using a formula here, this isn't too difficult. So the Laplace transform of cos 6t, we're just going to use this formula, is s over s squared plus 6 squared, which if we want, we could say is s over s squared plus 36. Okay, now we have, I think, something I'm going to put in the next video.